All right, then. So there we go. Started the recording. I didn't forget like I did yesterday. That's good. Hi, everybody. Welcome to the second talk from the week, our Women of Science Week, our 9th annual Women of Science Week. Thank you to those who are in attendance virtually and those who are in attendance in the class. I'm sure we're going to have an excellent talk for you guys today. So without further ado, I'm going to introduce Maclean Rouble, who is a PhD student in physics at McGill. And her work focuses on instrumentation for millimeter wavelength cosmology telescopes, which is something that I don't understand, but I'm hopefully going to understand much better by the end of the talk today. And in particular, the South Pole telescope, which is really cool, and similar experiments. In this talk, she's going to discuss the ins and outs of working with technically minded research communities and how we detect science signals and what it means to see something from the very early universe, and also what it's like to work at the geographic South Pole, which is something I'm really eager to hear about. She's also going to describe her own path into physics and share some advice on how you can get involved. So again, if you have any questions, I'm monitoring the chat. I'm monitoring the participants for those who are online, so you can raise your hand at any point or put something in the chat. If you're in the classroom, raise your hand, and Nick or Lisi will identify that and flag it and interrupt at an appropriate point. So ask away if you have any questions. Otherwise, Maclean, thank you very much for being here, and take it away.
Thanks. Hi, everyone. I have some slides. Let me just share those. If ever you can't hear me either, please shout. My microphone is known to be a bit dodgy. So, right. Thanks for the great introduction, Carl. As I said, my name is Maclean. I'm a PhD student at McGill University. I currently work with the McGill Cosmology Instrumentation Laboratory, which is a lab research group within McGill. We do a lot of focusing on construction of instrumentation for millimeter wavelength cosmology, which means I spend a lot of time thinking about how to see things that we can't usually see. So that's what I'm going to talk a lot about, what I mean by seeing. And this might seem like a kind of obvious question, but when you start to really dig into the essence of what you mean when you say see something, especially something that you can't regularly see, like with your eyes or with your phone camera, you have to really think about what this means on a fundamental level and how you can change this. And that should lead into a little bit of discussion about, what is cosmology? What are we trying to see in the end? What is it that we can't see right now that we're interested in? And my group does a lot of this from the geographic South Pole. So I will show some pictures from that and describe the work that we do down there. But first, a bit about me, I guess, before we get into all the really interesting stuff. I'm a PhD student, so I'm working on my second graduate degree. A long time ago, I finished high school in 2010 in Ottawa, Ontario. So I didn't actually get to do the SageUp experience. I'm quite jealous of you guys. It seems like a very good program, and you guys start off on a really good foot from that. After high school, I took a few years off, so I have a little less linear path into science than many of my colleagues. I worked in bars, did the usual thing right out of high school. But then after I decided, I like physics because I've always been a nerd at heart. And I went back and did my undergrad from 2013 to 2018 at McGill, physics with a bit of computer science. And then in the upper years of my undergrad, I started to get involved in research projects with groups in the physics department and around. And I found that I really liked it, and that, when you like something, you get good at it pretty quick. And so I found a place for myself there. Still on Team McGill, I'm still there. And so now I'm working through my PhD, and I hope to finish up another couple of years. Having a great time. In the meantime, I've joined with the South Pole Telescope collaboration, which operates a millimeter wavelength, or we might say a microwave wavelength telescope at the geographic South Pole. So this is helpfully labeled because this is the telescope itself, and this is part of the collaboration standing on it down at the station. And that's me on the left there, in case you couldn't tell. But okay, so let's get to science first. So going back to this obvious quote unquote question of seeing, let's ask about this. So what do we mean by see something? Firstly, we have to know what is light, right? And then also what is seeing, like what happens when you see something, what is interacting, what's happening with the light in your detectors or your eyes when you see something, what things do we see, what things don't we see, and why for either of those options. And so really, like, this quickly becomes a little bit more complicated than it was just at the first glance. And so to try to start to answer this, it's good to like take it to like break it to the most fundamental level. So two key aspects here about seeing things. Let's use the example of our typical human eyes. Not every human eye, but most human eyes work as light detectors. And what happens here? So they have to catch the photons, right? The light's out there. The lights actually have to get into our detectors. If the light doesn't get into our detectors, we're not going to see it. Nothing else is going to matter here. We have to get the photon into our eyeball. A good example for this is thinking of a laser pointer in a classroom. If a teacher points a laser pointer at the board, you don't see the beam of the laser as it goes from the pointer to the board, but you do see the dot on the wall. And you see the dot because the photons bounce off the wall and they bounce into your eyes. And so you seeing that dot, you might think, well, okay, I can like follow the path that those photons came, like bounce off the wall and they go back this way. And you can deduce that there has to be a beam there, even though you can't see it yourself because the photons in the beam aren't going straight into your eyes, they're bouncing first. And so you're using this deductive reasoning to think, okay, well, there must be a laser pointer here because I see it bouncing there. And that's sort of the same line of reasoning that we use a lot in astronomy. We can't directly observe some things because they're far away or because they're small. But we see their photons as they bounce off something else, or we see the influence that they have through photons that reach us on their surroundings. And so that's the first essence. The second essence is to be able to resolve something, or to resolution. You might think of this in terms of like your camera screen, your computer screen, or like when you adjust the focus on a camera, you bring things in focus of one part, they're nicely resolved and crisp, and other things are blurry in the background. And that's one type of resolving. But if we go even more basic, the key aspect of resolving something is being able to tell that it's there, to distinguish it from its environment, from its surroundings. So, to a good example of this that I noticed a lot when driving is if you see a car that's a long way away at night, it's got its headlights on. But when it's really far away, it just looks like one headlight. It's just one light way over there. And that's because it's so far away that the distance between, or the apparent distance, the angle, if you will, between those two lights is very, very small. And it is smaller than what my eye can resolve. As the car gets closer, you start to see the two headlights to be separate. And it's at the point when you can distinguish them from each other, that there's two lights there as opposed to just one, that we say we've resolved them individually. So two main aspects. Let's talk a little bit more about resolving, and also a fun nerdy party trick if you would like. Fun question is, can you see things from space? So imagine we are this astronaut and we are trying to see these car headlights. I'm going to hazard a guess right now that our eyes as human eyes are not able to resolve those car headlights. But let's prove this to ourselves, right? Let's just check. So when we sit here, the key thing here is the distance between the lights themselves. So that distance doesn't change, right? The car is always the same size, but it appears to be smaller because it's very far away. But the angle between those lights is smaller when it's further away. Distance is smaller. Everybody remembers trig, right? Not to give anybody math flashbacks, but this is the whole relation you need. And so us, near the International Space Station, we're up 400 kilometers roughly away from this car. We look at the radius of the car, or the distance between the headlights would be twice the radius, so the diameter, and we apply the tangent. And we take for our angle here the resolution of a human eye. And so this number, I didn't measure it myself. This is from the literature. I'm not a biologist nor an ophthalmologist, but the human eye has a resolution roughly of about 1 arc minute. So that's 0.016 degrees, which is actually surprisingly small. The human eye is an amazing thing, especially the ones that the typical human eye is pretty remarkable. And so we plug this small angle into our equation and we find we are 400 kilometers away. How big does that car have to be for us to be able to resolve its headlights? Unfortunately, it has to be at least 112 meters across. And so I think it's unlikely that we would be able to tell those car headlights apart. But you can use this if you want to say can I see the pyramids from space? And you just check the size of the pyramids, and they're about 200 meters on each side. And so you could guess that an astronaut on the International Space Station could look down with their typical human eyes and would be able to resolve the Great Pyramid. I suppose another issue that we might encounter, though, maybe not in the case of the Great Pyramid, but certainly in the case of the car headlights, is you have to catch those photons. Remember our point number one, like photons have to get from the car to our eye. And at that distance, that might be tricky. So considering what happens when we catch, when we're trying to see something, we have to catch the photons. These photons are emitted by their source, or they're bouncing off of their source, and we have to catch them in our detectors. So our detector is a photosensitive thing at the back of the eye, and there's a hole that lets the light in. And so the pupil, right, the hole lets photons in. The photons hit the retina on the back of the eye, where they are absorbed mostly. For the most part, the more the better, but most of them are absorbed. And once they get there, they trigger a biochemical electric reaction that is certainly in somebody else's field of study, but not mine, that does some magic as it reaches our brain, and that allows us to perceive this. We see it. Like, this is the detection aspect. So the photons have entered our eyes and we are aware of it, and we use this to paint a picture of the world around us. Now, we could imagine some improvements to this might be in, if we can only catch a certain number of photons because of the size of our eye, we would do better by being able to absorb more of them. So you might think of like your cat's eyes. Cats are known to have really good night vision. Do you guys know offhand why they can see better in the dark? What is their improvement on their eyes versus ours? I guess it might actually be difficult to see hands. So if you want to shout it, please shout it. But otherwise,
But someone who wants to give it a try.
So
yeah, please.
said that this is kind of relating to photons being mostly absorbed. Maybe the retinas are better, so the lights let in more effectively, so they can see in the back.
Yeah, exactly. Yeah, they're. Yeah, that is exactly what it is. Like, their retinas are just better designed than ours in a way to work in this low light environment. So they have this reflective coating at the back that the light comes in just like our eyes, but then it's bounced back again. And so they get to sort of like absorb the light twice. And so their eyes are about 40% more efficient at catching and absorbing photons than ours are. And so that's one, like, as we start to think of how can we make our eyes or our detectors better, there's one way, right? So the cat has made an improvement on this detector technology that we haven't quite enabled for ourselves. But we can do even better than this, right? Cats are cool, but we can be scientists. We can ask different questions, and we can get pretty creative with the things that we want to see. So, but when all this still talks about like finding the key questions to ask and then asking them to yourself. So here's another set of key questions, and let's like stick with a bit of a method. So first up, when we want to see something, first, what do we want to see? We have to pick our goal here. Do we want to see visible light? Do we want to see a different kind of light? And why? What are we trying to accomplish? Once we've picked that, say visible light, right? The kind of light that we see all around us. How are we going to see it? Where is it? Where does it come from? Is there a lot of it? How are we going to absorb this light, right? What are we going to use as our detector? Like, is it high energy, low energy? Well, think about what the light is, and then design our experiment to see it. And then thinking a little further ahead, once we have done this, once we've found it and we've absorbed it, there's that other key aspect that is the detection, right? For us, that's our brain processing those light signals into a vision or something that we see in front of us. But a telescope doesn't have a brain. So how do we design our detector to tell us when it has gotten a photon, and how do we get any information out of that photon once we've got it? This lovely telescope that's in this picture here is the Hubble Space Telescope. And so in answer, for example, to the first question of what type of light do we want to see, thinking of the same kind of light that we see with our own eyes, visible light, we might build something like Hubble. Hubble is an optical telescope, so it sees light like we do, although it does it a little differently because it is not human. But it also has taken some steps to improve the way it sees visible light. So Hubble is this Hubble Space Telescope because it's in space. And the reason it's in space is, although there's a lot of visible light on Earth too, as we know, most of us see it all around us all the time. If you're trying to see things in space, if you want to do astronomy, those things are far away, and compared to the light that's on in the room right now, or compared to the sun, those things are not very bright. And so being on the ground, you have all this air around you. You have a lot of other lights, like, you might live in a city where it's hard to see stars at night. You have daytime when the sky is blue and not transparent. So it's just better if you could just avoid that whole situation. You just leave the atmosphere behind. And then once you're in space, you don't have to worry about light pollution. You don't have to worry about the twinkling of the stars because the layers of the atmosphere diffract the light that comes through them in different ways. And so there is a sort of an extreme example of how you might improve your ability to see visible light, but nonetheless a very effective one. And I'm sure we've all seen beautiful images from the Hubble Space Telescope. And in fact, the faded background on many of my slides is a picture taken by Hubble of very, 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 very distant galaxies called the Hubble Deep Field image. And it's able to make such lovely images because it has left the atmosphere behind and is in this pristine environment. But I'm not an optical astronomer. Optical astronomy is extremely cool. I look at stuff that's a bit weirder. And so let's dive into that a little. But first, a small recap. So light is an electromagnetic wave. So it is a disturbance that travels through space. This disturbance is in the electromagnetic spectrum. So it's a fluctuation in the energy in the electric field and the magnetic field that are tied together, and it travels at some speed. And it oscillates. The speed at which it oscillates, so like the distance or the time taken to complete one full oscillation, which is what's pictured here as the wavelength, the shortness or the longness of this wavelength determines its energy, and its energy determines its characteristics. And as this lovely diagram from the Encyclopedia Britannica shows, what we use it for, because light is very useful, right? Most of us see it with our eyes, but we use it for a lot of other things too. Gamma rays, well, actually, I guess we sort of try not to use them too much in general. We stay away from gamma rays, but X-rays, you break your hand and you get a nice X-ray taken. These are higher energy things and can be kind of dangerous because they're so high energy that they can disrupt our cells. Going a little lower, ultraviolet rays can be harmful, but are much less harmful than, say, gamma rays because they're lower energy. And if you go further down the spectrum to lower and lower energies, eventually you get down to these really long wavelength things, like kilometer long wavelengths, which is like radio waves that we use to listen to the radio, if anybody listens to the radio anymore, or to make distance measurements. Radio waves are everywhere. We don't even see them. Like all these other kinds of light, they're all around us all the time. We don't see it at all. But something does, right? The radio sees the light. How does the radio see it? Just because we don't see it doesn't mean it's not there. It doesn't mean it's not useful. It just means that people like me and my research group had to spend time thinking about, here's a type of light I want to see. How can I see it? And in particular, what we want to see are microwaves. So just a little bit higher energy than radio waves. We say millimeter wavelength because in general, the wavelength of this light is about a millimeter long. Called microwaves because they're small, I suppose, although really on the scale of things, they're quite large in wavelength compared to some of these higher energy things. But I think it might be a misnomer from the past. Now, microwaves, this is the same kind of radiation as is in your oven. We cook with these, so they're very useful, but they occur in nature too. They're all over the world. They're all over space. And so we build telescopes to see them. For example, the South Pole Telescope, my favorite. This is a microwave or a millimeter observatory that we've constructed at the geographic South Pole. So we've answered our first question, right? Remember our 3 key questions? What kind of light do we want to see? We've decided it's microwaves. But then next up, we still have to answer those other 2 of how do we see it and what are its properties? How do we know we've seen it? So how do we detect it? And then I'm going to add one more to this list, which is once we have it, what do we do with it? What's next? What's the science that we can do with it once we get it? So first up, question number 2. What are microwaves? What about them? What are we going to use in their nature in order to be able to detect these things, right? There's lots of them. They're all over the place, but they're kind of lower energy. These wavelengths are kind of long. These millimeter wavelengths, that will dictate the size of the detector that we use to see them. Generally, if you want to absorb a photon, your detector has to be sort of at least as big as the wavelength of the photon. So you think of a radio antenna on your car is like a meter long or so, and that's because the wavelength of the light it's going to detect is on the same scale. And so for us, we need to build detectors that are about a millimeter across if we want to pick up these microwaves. Now, we want to see microwaves from space, not microwaves from our oven. So we have to go somewhere where firstly, there are not very many microwave ovens, but we also need to be careful about where we place the telescope, because thinking of ovens, microwave ovens, they interact with water, these waves, and which you might be familiar with as like if you put like a pizza pocket or something in the oven, or like a hot pocket, it's the inside where all the sauce is, like that's what gets you when you bite into it. The outside is dry and maybe still frozen, but the inside is burning hot. It's because these microwaves interact with water molecules and they really heat up the water. So this is great for cooking things, but it is not good for seeing microwaves from space, because there's water vapor in the atmosphere and we're trying to see these waves coming in through the atmosphere. And if the waves are getting caught up interacting with the water in the atmosphere, we're not going to see them. We want them to interact with us, not the air. And so we put our telescope at one of the driest, if not the driest places on Earth, which is the geographic South Pole. This has the extra advantage of being quite far from most microwave ovens, but also quite far from Wi-Fi and cell phones. And although I love having cell coverage as much as anyone else, this is a huge problem for astronomers because they use the same frequencies and they're very, very bright. And so we're trying to see these faint signals from space, and it's kind of the same analogy as trying to build the Hubble Space Telescope in downtown Montreal. If you have all this light pollution all over the place, you're never going to see the things that are coming from space. But fortunately, yeah.
Are there other sources of microwave other than microwave ovens like on Earth?
So like all cell phones, Bluetooth, Wi-Fi signals, like most communications technologies these days, more and more. So we have to be, the regular radio stations are down in the radio waves, so they're a little lower energy. But once you start to get into basically all your computer, Bluetooth signals, all that, it's all right in the same wavelength range as we're trying to observe from space.
And how about other than human generated sources? Are there other sources of microwave on Earth?
Oh, that's a good question. So because light is emitted as a spectrum, most things emit over a wide range of wavelengths, but to different extents. So you might get really hot things that will emit at higher frequency, higher energy light, and cooler things lower. I don't offhand know of any things that like emit only microwaves that in nature on Earth, but that's definitely not to say that there aren't any. That's a great question. I'll have to think about that more.
Good question. Got a question, if you can hear me.
Yeah, go for it.
Is giving off the microwaves that you're wanting to look at.
Sorry, I couldn't quite make it out what you said.
That you're trying to look at. So I appreciate the land-based detection, but what is it in space that you're trying to detect?
Oh, okay. Well, don't worry, we're getting there. I will answer that question, I promise. But first, we have to figure out how we're going to see them. Yeah. Good question. I will just like 3 more slides, and I will get right into it. It's not necessarily a straightforward question, so I want to approach it from a way that that makes sense. Are there questions too before I get into what we're looking for? Great. Okay, so having put the telescope way down in Antarctica, away from Wi-Fi and cell phones, the big human-generated sources of microwaves on Earth, we can start looking up. Right? We want to catch these microwaves from space. The question then is for number 3, how do we catch them and how do we know that we've got them? And so as you may know, we don't see microwaves, right? When you look into your oven, it's not glowing. We can't see them with our eyes. And so we have to design different types of detectors in order to pick them up. And so we use basically thermometers, like very tiny thermometers, a microcalorimeter is a tiny, tiny thermometer. We make these big arrays of them inside the telescope. We keep them very, very cold. And when they're this cold, when a single microwave photon comes in, it warms up the detector just a little bit, and then we see that change in temperature. And so we know that we saw a photon. If it warms up a lot, it tells us either that we saw a lot of photons or that we saw a very high energy photon. And if it warms up a little, it's the opposite, just 1 photon or a lower energy. And so by monitoring the temperature of all of these little thermometers, we can then get a picture of what's coming in from the sky. And in practice, this looks like this. So this is one of our detector wafers from the South Pole Telescope. This individual wafer has about 1,600 to 2,000 detectors on it. There are 10 of these wafers inside our focal plane, so inside the main camera of the telescope. And then we cool these down to about 1/10 of a degree away from absolute zero. And when they're at this temperature, even though microwave light is quite low energy, it can actually make a difference in their temperature, and we can see that. And that's how we detect things. But now to answer your question. so we have the photons now. What's next, right? What is the science that we're going to do with this? All of this development is also a branch of science. This is instrumentation science, but now we're going to get into the cosmology side of the science. So now we ask ourselves new questions, like, where did we get the photons from? Did they come from a certain direction predominantly? Did they come from a certain distance? Remembering that because light travels at a finite speed, if it has been traveling over a long distance, it's also been traveling for a long time. And so the further away you look from us, the further back in time you're looking. So important to know, how old are these photons? Also, like, what is their intensity? How many of them are coming in, and from what direction? And then finally, we want to know their energy, or like things about them, their characteristics. Are they polarized, or are they all aligned along the same axis? And once we have all this information, we can then paint, if you will, a picture of the source of them. And we paint kind of a weird picture. And so I will show you the picture first, and then we'll explain what's actually what's happening in this picture and why we care. But first, the mechanics of this. This is a full sky projection. So you imagine like this as a sphere around your head, but then flattened onto a page to show it. So this is kind of like when you see those globes, like the Earth flattened, and it's all a little distorted around the edges. But this is an image of the entire universe all around us, but without any of what many people would call the interesting things, like without most of the matter, without the stars, without the galaxy, without the planets, without the dust. This is just the backdrop of the universe. And of course, these colors are, it is not blue, it's not red. We've colored it this way in order to help our eyes distinguish between different variations in the temperature or in the energy of the light in different areas, which is a sort of fair analogy to do because, you know, when we see visible light, the colors there correspond to variances in wavelengths as well. And so we've just transposed that down into this microwave light, but this is all microwave light from space, from way out in space. But what is this? This is not a very clear, like there's no, you know, nothing jumps out at you, nothing jumps out at me anyway from this picture. So what are we looking at? This is called the cosmic microwave background. This is like one of the key focuses of modern cosmology, so the study of the beginnings of the universe. And it's this key, the beginnings of the universe, that make this light particularly interesting to us. This is the oldest light in the universe. It was emitted 380, roughly 1,000 years after the Big Bang, the very first time that light actually could be emitted and then keep traveling. And to understand that a bit more, we have to kind of look at the history of the universe. In just a little bit of time, though, don't worry. We won't go through it in too much detail, because I guess you could spend 13 billion years if you wanted to tell the whole story. So 13.5 billion years ago, we have the Big Bang, the starting moment. The universe is infinitely small and dense, and it explodes outwards. And this very first period, this is a very interesting period of the universe, right? The Big Bang, what? Like, oh, this sounds like a black hole. What is happening? What happened before it? Nobody knows. And if anybody tells you they know, they're wrong. They're lying. We don't know. And what happened right after the Big Bang is this, we think, this period of very, very, very fast expansion, very short, like less than a second. And the universe went from infinitely small and dense to big, like almost the size it is today. And we call this inflation. And this also is extremely mysterious. How did this happen? Why did this happen? The laws of physics as we know them today don't really explain what went on in this time. And so do we need to develop new physics? Is this the answer? Like, is this where we'll find the answers to the grand unifying theory? It's such this extreme period of time in the universe where energies are so high. We can learn about particle physics. We can learn about astrophysics. We can try to figure out new laws of physics and unite quantum. Like, it's very interesting. And I know I'm biased, but it's a very interesting period of time. But we can't see it directly, like not just because it was a long time ago, but because the universe was opaque to light back then. It was so hot and dense in this sort of cosmic soup phase where protons and electrons were not even coupled to each other. There's no hydrogen, they're just all around, and photons are all trapped in there. It's all hot and dense, and the photons that would become the CMB, the cosmic microwave background, eventually are trapped, and they just keep bouncing, or what we call scattering, off of other electrons and protons inside the soup. But over time, after about 380,000 years, as it would happen, the universe had expanded enough that the protons and electrons could begin to couple up. And so we get hydrogen nuclei forming, the universe kind of cools a bit, and then finally, these photons can travel freely. This period is called recombination. I've never really liked this term because what is the re here? They weren't combined before, but whatever. This is what people older than me have decided to call this period. And so once this recombination happens, the light can travel. So it bounces one last time, or it scatters one last time at this point 380,000 years ago, and then it just travels freely through space. And so we call this, because we perceive it as a surface, because it happened at a sort of a certain time away from us, and that is a certain distance away from us. This surface of last scattering is where the photons, they bounce one last time, and since then they've just been traveling through the universe until we absorb them with our telescope or with our skin when they hit us. These photons are everywhere. They're extremely abundant. This is one of the brightest things in the sky, that if you could see microwave light, you'd see this everywhere. And so it's kind of neat to think that these photons have been traveling for almost 14 billion years, and then we absorb them, and we make these weird looking maps like the blue and green marble I was just showing. So thinking again of this image then, what is this then? That's where those photons came from. But what am I doing with this picture? Why are we interested in this at all? What can I learn from these photons? I can't go to the very early universe myself. That would be cool. Maybe it would be fatal, but it would be interesting, that's for sure. But because I can't, all I can do is look at the photons that I can collect from it. And this is because it's the furthest thing we can see. Remember, the universe is opaque on the other side of this, and maybe I want to know about inflation, what happened before it. But this is the oldest thing we can see. I can't see inflation, and so all I have is this, and this will maybe can contain clues as to what happened before it. So, in that cosmic soup phase, what happened in there? What happened during inflation? What happened at the Big Bang? What happened before the Big Bang? And one of the biggest things that jumps out at you looking at this, I think, or at least the first thing I notice, is I wonder why is it spotted? Why are there areas that are redder than others or bluer than others? We've colored those to correspond to hot or cold regions, but why do they have this pattern? And the big surprise really of these images is, why are they there at all? When you think of the early universe, like the very early universe, the Big Bang was infinitely hot and dense. And if something is infinitely dense, surely there can't be regions that are more dense than other regions. There can't be regions that are more hot than other regions. And so why does the universe now, which has just expanded evenly in all directions, why is it not uniform? Surely I would have expected this to just be flat and smooth. And so the fact that these patterns are there at all is quite interesting. And a lot of modern cosmology, especially people like me who build telescopes to look at this light, spend a lot of time making very, very, very detailed maps of these different fluctuations in the temperature of this light. And we try to make inferences about what happened before, because we can't see what happened before, but we can see the echoes that it's left, or the remnants of this cosmic soup just painted all around us, all over the sky. So we, for example, our telescope, the South Pole telescope, we take maps, right, like this. We zoom in on a very small part of them, which is the top image here, and then we zoom in even more. And so the bottom map here is a map from the South Pole telescope of a very small region of the sky at the same wavelengths, same type of light, and we get even more detail. We zoom way in, we look at it for a really long time, and we catch as many photons as we can. And you can see that we really do see a lot more in detail there. So much so, in fact, that if you look really closely, you might notice that there are these little white and dark spots on the image, which look a little bit like a broken pixel or something. Those aren't broken pixels. Those are galaxy clusters. So to give you a sense of scale here, this is so far away that these galaxy clusters, which are the largest structures in the universe, it's hundreds of massive galaxies that are all circling each other, megaparsecs across. They show up as single pixels here, cast sort of as shadows or as bright spots against the background that lies behind them. And so we see a lot in these images. The patterns in the background itself, these dark and light regions, we look at the size of the variations, like, oh, is this a wave? What caused that wave? Or why is it denser here? And it's through making maps like this that we hope to get a better understanding of what's going on in the early universe.
I've got a question.
Yeah,
Those pixels be dark instead of light if they're galaxies?
so that's a great question. And so some of them are dark and some of them are light. Some of the reason that some of them are dark is because they're not emitting in our band. So compared to in our wavelength, so compared to the microwave background behind them, they emit less microwave light. And so they appear dark to us. But other ones actually do emit at our wavelength. And so they're brighter than the background. And so we see them as bright spots. So those galaxy clusters, for example, like if you look at the optical image, that's actually the background of this slide. These are optical galaxies and they're shining, but maybe some of them are not shining in microwave wavelengths. And so these might be bright to see them with your own eye or with Hubble, but with our telescope, they show up dark. Yeah, good question. So a lot of what we do ourselves, talking about stuff, and what we do, I will say up north when we are, in our home universities, our home institutions, we want to improve things. So we want to see more detail, right? We want to take maps like this, but like go even more and see every tiny fine structure inside that we can, get all the information we can. And to do this, we need more photons. We always need more photons. But to do that, we need new telescope technology. And so we spend all this time thinking about like how we start with those three basic questions. What do we want to see? How are we going to see it? And like, how do we know we saw it? And we just iterate and we try to make detectors that have, or we make cameras that have more and more and more detectors because, the more eyes on the sky, the better. And of course we have to test them and we have to build the electronics to operate them. I mentioned briefly before that these detectors operate at a fraction of a degree away from absolute zero. So it's not just something that you can have on the bench. Like you can't just have this on your desk at home and shine a microwave light on it. You have to put it inside a cryogenic refrigerator. So the left image here is the current camera that's in the South Pole telescope. So it's 10 of those wafers that I showed you with all the pixels on them all together covered in a lens. But to test something like this, we put it in a device like this on the right-hand side, which is a cryogenic refrigerator. This is the test setup that I work with a lot at McGill in our lab here. And when this is open, but we close it up eventually, we seal it all up, we put our detectors inside, and then we cool it all the way down to 30 millikelvin, so 0.03 Kelvin, or minus 272 point something. Arithmetic is certainly not my strong suit. But this is how we test the things. This is how we design. And we spend all this time working with different collaborations across Canada, across North America, and around the world, who all do different aspects of this design. I don't personally build the detectors. I build the electronic systems that get the signal from the detector, which is very, very cold, all the way up to room temperature where I am and where my computer is. And so then I can do the science. Once I have those signals from the detectors, I can do the science. So we call that the readout. So we're reading the pixel out to room temperature. But of course, that's not all we do. Once we've done all this testing, we have to actually operate it. And so we have to bring these things down south, way down south to the geographic South Pole. The South Pole telescope was very creatively named. It is at the geographic South Pole at the Emmons and Scott station. And we go down ourselves. We bring these things that we spend years building and years testing and years thinking about, and we carry them down on airplanes very, very gently, and we install them ourselves in the telescope. And so that's what this picture here on the right is showing, is a few humans working up on the telescope. The telescope itself consists of this big main dish here at the back, which is the primary mirror. We call it what microwaves from space come in and they reflect, and they go into this arm that this fellow in black is standing on. And this is the receiver arm, and that's where the camera is. So this focal plane is inside the camera, and it lives inside this big white structure. And this whole thing moves. Like it's tipped down so we can climb on it, but like it all goes up and it turns and it looks at the sky. It moves shockingly fast when you're close to it. It's a 10-meter dish, so it's imposing. It's a very neat experience. On our way down there, we see some amazing things, even though we're going down to see amazing things from space. Even just traveling to the South Pole, you see incredible stuff. You know, it's all ice runways, and we take off from an ice runway and you land on an ice runway. There's, of course, snow everywhere and amazing ice in the sky. But the things we do when we're down there, we spend a lot of time like in the telescope. So these are some pictures inside the telescope. So for reference, on the right is an outside view. This is sort of from the bottom below the dish looking up. You can see the receiver arm here, which is where the camera is. And we climb up inside there. So that's what this thing on the left, this picture on the left is showing. You can actually get up. It's about human sized, maybe 2 human sized. And if you're not afraid of small spaces, you can clamber on up in there and you can work on the readout electronics, or you can adjust the mirror. You can see there's a little bit of light coming through in the middle. That's the aperture where it actually sees out into the world, because it's enclosed, which is nice because it's very cold in the South Pole. So we keep it a little warmer inside the telescope. We also have to do, maintenance tasks. We have to point the telescope around. You can drive it by hand, which is kind of cool. You use this control computer, you type in its coordinates and it rotates, and you point it at certain things to calibrate it. But you have to grease it. It's a machine. It's made of steel. And so every couple of days we climb up into the gears and we like slather on grease all over. And it's very like hands-on science at the like most interactive level in a way that I wasn't expecting necessarily when I first got into physics, but it's very cool. While you're down there, at the South Pole Station, we're not the only experiment. We are one of several big ones anyway. There are other cosmology experiments down there, like the BICEP or Keck array, which is these left and right pictures. Because it's such a great place for microwave astronomy, because the air is so dry, other experiments have also decided to take advantage of this. And so we have many friends, if you will, who look at similar types of light from space, because it's an excellent opportunity, an excellent location. There's also the Ice Cube Neutrino Observatory. Here's a picture of the inside of their server room with a truly terrifying number of cables connecting all of their detectors together. And this is a neutrino observatory that uses the ice as its detector. And so it hangs all of these light sensitive things in through a kilometer deep of ice. And when neutrinos come in, they glow. And so they see it as optical light as the neutrinos pass through the ice. So these are amazing experiments. So getting to go down there, you help out a lot with, a lot. As much as you want, you can help out with other experiments. You get to visit their facilities. You get to meet all these scientists from all around the world who are doing amazing research. And like crawl up inside telescopes. Where else you get to do that? Of course, there's other things too. We spend a lot of time shoveling snow. It's just covered in snow everywhere. And if we're not careful, we'll be buried in snow. So we spend a lot of time digging out snow, not always with backhoes, with shovels too. It takes a lot of time, but you meet amazing people, you make a lot of friends. There's not a lot of stuff around you. That's just the station and then ice for 1,000 kilometers to the coast. And so, the people you're down there with are your resources, but also your friends and your family. And you've got to stick together for warmth, but also for company. But you make some friends who aren't human too, like penguins. This is one of my favorite friend encounters near the coast on the way down at McMurdo Station. There are many penguins that hang around and they're adorable. I was very taken with the penguins. But big picture here, thinking about like how did I find myself in this situation to be able to do these amazing things and to see these amazing things from space? I think the key thing here is that I find these things amazing, and because I do, it just really excites me. I'm an excitable person. I'm curious about this stuff, and because I'm excited about it, I'm happy. Like I really work on it, and it's fun for me. And I can imagine that if I wasn't as interested in it, it wouldn't be nearly as fun. I wouldn't want to work on it as much, and I probably wouldn't be as good at it as I am. And so I think if I'm trying to think of a way, like sort of, let's go back and find out like 3 basic rules for being good at science. I think the top one is that find something that you care about. Science is a lot of work. And if you don't like what you're doing, then it's not worth doing. You should find something that you actually care about. You also need to be very curious. Like, you ask lots of questions, especially the basic ones. This whole talk has been, let's ask very basic questions and then get really complicated answers. That's all science is, right? You've got to, if something even seems obvious to you, question that. Why is it obvious? Is it obvious to other people? Maybe somebody understands something in a way that you don't. Or maybe somebody doesn't understand something at all. And that's the best opportunity for you to talk to that person about something that you understand. And then you can go back and forth and you both learn from this. And then finally, kind of on the fun side of things, like, make a lot of focus in science, especially as you get in through university and into grad school. There's a lot of pressure to have really good grades. And it is important. It does help to have good grades, but it's not everything. You should, like, I personally had kind of crappy grades through my undergraduate work. And that has made it a lot harder for me to progress through academia because, scholarships or applications want to look at your grades. But the route I found through this was that because I enjoy these things, have some personal projects on the side, and I was able to meet people and talk to people and ask them questions and talk about these projects that I was working on. And through that way, I could start working on these other research projects. And through that, I've built up a pretty diverse skill set. And in general, I find a lot of researchers who've taken that kind of path, or who have the approach of being really interested or having a lot of other hobbies that they do on the side that, like, may or may not relate to the science they do. They're really good scientists. And so there's a lot of different routes into this field, but I don't know, follow your heart, I guess, is what I'd say. Find something that you care about and go for that. And that's about it. So if you have any comments or questions, I love questions, or you just want to reach out if you don't want to do it in front of the class, you can send me an email, but yeah, it's been great to meet you guys and share pictures.
Wow, that was weird. Wow, thank you. No, not you. My screen just decided to have a little stroke there when I
I'll take weird. That's fine.
clicked my mute button to start speaking. Went brrr, but now it's okay. It's good. Thank you, Maclean. That was terrific. I'm monitoring the chat here and participants online. I don't see any questions right now, but I'm going to open it up to the classes if anybody has any questions for Maclean.
Maybe
While we're waiting. Oh, go ahead, Nick. Wasn't Nick,
Nick.
it was Lisi. Sorry, go ahead.
I have two questions. The first is how much time would you spend at the station at a time in the South Pole?
So it really depends on when you're going down there and what you're going down there for. So the Antarctica, like the Arctic, has two seasons, summer and winter. And during the summer, it's daytime, and during the winter, it's nighttime. And during nighttime, it's extremely cold, so cold that they close off the station permanently. So from February, which is the beginning of the austral winter, until October, no flights go to the South Pole. And so the people who are there stay. And so that's called wintering over. And so people who winter over usually will go for about a full year, and they're just there. And during the winter months, that's kind of it. It's you and about 40 other people, and you operate, a couple of you work on telescope, other people cook food, other people work on other telescopes, and you're there for the whole season. If you're going down during the summer, which is what I did, as you can tell because it's daylight in my photos, usually go for a month, 2 months, and that kind of thing. It takes a long time to get there, so it's worth going for an extended stretch, but you usually go down with some specific mission in mind. You're going to install this thing on a telescope, or you're going to learn to do this maintenance task or something. And so you go until you've accomplished that, and then you help out a bit, and then you come on back up north.
Awesome, thank you. And the other question, I don't know, it's more about the microwaves you're catching. You said that you're trying to catch these microwaves that were emitted at the beginning of the universe.
Yeah.
What I don't understand is that if they were emitted mostly at the beginning, aren't they now like at the borders? And since we are not at the border, how do we catch them?
Right. Yeah. Great question. So the border is still there, right? And so that's what we see when we look out. But because they were emitted so long ago, they've had all that time to travel to us. But sort of, you can think of it in the other way around, is that because they've had all this time to travel to us, to travel all this distance, the border is still out there. And it is like, you look all the way back and we see them. And when we see them, we are seeing that border all the way far away. Even if it happened so long ago, we sort of see the echo of it now as those photons finally make it to us. And so as more time goes on, the photons that we see from this border come from even further and further away, even further and further back in time, because they've had even more time to travel. And so a less extreme example would just be that, if you threw something really, really, really far, like to the moon, it would take a long time for it to get there. Like even if you shine a light at the moon, there's a delay. And so whoever's on the moon sees that or catches that ball or like sees the light you're shining at them. But the light they see, those photons were actually emitted a second or two before, or in the case of something that you've thrown, probably a few days before. And so it's that delay between these things that is what lets you sort of look back in time when you look far away with light.
So we are seeing the reflections of these microwaves.
Yeah, the remnants of them, or we're seeing what the universe looked like when they were first emitted.
I have a question for you. I have a couple of questions for you. Go to the technical one first. So you mentioned, and this was a great question from someone in Nick's class, I think, with that image where there were the little dots that I thought were weird pixelated things too, and apparently are galaxy clusters. So yeah. But what makes an entire galaxy cluster not emit microwaves at the same level and others emit so many that you get this distinction between them?
That's a really good question. There are a number of effects at play. Mostly what you see when you look at a galaxy cluster is the sort of the gas in the cluster. So each of the galaxies is there and we can't resolve them, right? They're too close together for the resolving power of our telescope. We just see that dot. But there's a lot of galaxies in there, but there's all this dust around in between them. And that dust is sometimes extremely hot because there's a lot of magnetic fields. These galaxies are like flying around each other. It's just crazy energies are involved. And the gas can really heat up. And when it heats up really far, it shines brightly, but it shines at different wavelengths. And so depending on the temperature of the gas, it may shine at some wavelengths, but not others. And so because all these different clusters are different temperatures and have different dynamics, we can actually learn different things looking at how bright they are in our band. This is through an effect called the Sunyaev-Zeldovich effect, which is actually one of the main, it's not something I personally work on with the South Pole Telescope, but some of my collaborators, their main focus is taking data like this, maps like this, and finding all of the clusters and then looking at what they emit and like where they are and trying to figure out stuff about the clusters and making a map of where these clusters are distributed throughout the universe. Because they're so big and there's so much matter in them, knowing where they all are, and like there's probably 100 or so just in this image alone, you can see a lot of them and you can trace out how this structure, these huge structures formed in the early universe. And to go back to your question, from their color, like from how bright they are in our band, we can then tell extra things about them, like how energetic they are and how fast things are moving.
Awesome. Well, before I hog all the time, are there any other questions out there? Okay, so I'll ask my next one. So this is a women science event. I'm curious, you're going down to the South Pole and you're spending large chunks of time there with a group of people who are all sitting down there all together, some of whom are spending an entire year cooped up together. How many of the people down there are girls or women? And what's it been like for you as a woman in this scientific field in such a, I don't know, such a closed environment?
Yeah, I mean, certainly I'm not in the majority, but it's the physics, especially astronomy, is moving pretty quickly towards higher levels of gender parity than many of the other fields of science, which is great. Within the collaboration when we're up north, or where we normally live, I'm not dramatically outnumbered by male colleagues. That is a little bit less true at the South Pole. During the main summer season, there's quite a few people there on station. There's about 150 people on station at any given time in the summer. And there it is, maybe 60-40 for women then. And that's kind of on par with science, I guess, or with physics in general these days. During the winter, I haven't personally stayed for the winter, so I can't speak to what the experience is like personally. Certainly there are fewer female people who stay for the winter than there are male, just based on the hiring and the population who's around. I have not heard tales of this being particularly egregious for the population who's there, although it is certainly known that some couples do form. Few of them last after the winter, but some do. Yeah, I think it's an intense working environment, I would imagine. And so of course, these things do happen, but because everything is so closed and you work together so closely with all of your colleagues, in general, I found that the experience is very fair and respectful in general. Yeah, I mean, especially I would imagine over the winter, like you're there, you can't leave. And so if you make an enemy with somebody or you are rude to one of your colleagues, like that's not going to work out super well for you in the long run. And so I think a lot of the time is spent like very carefully getting along.
Well, that's great. I find that very encouraging, what you just described.
Yeah, it's been very positive, actually. I was a little nervous because like you said, I like when you think of it, it sounds like I might be the only one, but honestly, the whole thing has been very positive.
No, that's fantastic. So you're going down there. How many times have you gone down there?
Just the once. I spent a month there last year. Yeah, as a newcomer into the collaboration.
Are you going back?
Yeah, I hope so. But I'm working right now. My main project is developing those electronic readout systems for the next generation camera to go onto the South Pole telescope. And so next year, tentatively, COVID abiding, we will be going down to install our new systems and test them out.
So you build up a fair amount of competency with this kind of technology and this kind of working environment. What comes next after this? I mean, is it just like you work on this telescope and you work in this environment forever, or is it like, oh no, we move off into some other field of research in astrophysics, or like what comes next?
It really depends. People from our collaboration who do similar things I do go on to do all sorts of things. Some leave academia and go into industry. You can imagine you develop quite a few practical skills doing this kind of work of building electronics and working in rugged environments. And some people will go off to work for like space development agencies and that kind of thing. Some people go off and do different types of science. Maybe they want to look at different types of light. Maybe South Pole Telescope is fun, but they're bored of the cosmic microwave background and they want to look at something else. The transition, especially from astronomy and with instrumentation, because you develop that broad research skill set, that these lessons that you learn from developing this technology or figuring out these ways to look at the data, to look at the photons you're collecting, are really applicable to a wide range of science. And so I've even had some friends who left to go work in data science and finance, like to just applying the mathematical algorithms they've learned throughout PhDs in physics. Weirdly, the finance is one of the biggest hirers for physics graduates. We go all over the place. Of course, you can stick with it. You can go on to do a postdoc on SPT. You can do a postdoc somewhere else, get a faculty job. It's up to you. Stuff is all over the place.
Another very encouraging answer. That's great. I don't find it surprising at all that finance hires extremely bright people who are excellent at math, frankly.
I guess when you put it that way, it does make sense. Yeah, that's true.
My last question for you is, where was the Canadian flag in your picture?
I know. Unfortunately.
Is it there?
Yeah. It's not.
Not?
I know. Canada doesn't have a large stake in the collaboration that mans the station. It's 21 countries, I think, are the signatories for the Antarctic Treaty, and the main maintainers of the station are the ones who make the biggest financial contribution are with their flags here. I know.
Oh, well.
Knowing this now, next time I can bring a flag. And
you bring a flag and plant it there, sure.
Yes, exactly.
Are there any other questions from the audience? Okay, well, if there's nothing else, thank you so much.
This has been great. Thanks for having me.
We really appreciate your time this morning. That was a terrific, extremely interesting talk. for me as a biologist, I found it extremely interesting, and I understood everything too. I think
Great.
there's probably a few things there I didn't quite understand, but it was really great. Thank you so much for your time. We really, really appreciate it. I will be in touch a little bit later, and we can chat later on as well.
Yeah, absolutely. And we've got the recording from this session, but I
We
can send you my slides as well. And so if anybody wants to reach out or look at the penguins, because like they're great, or other pictures that were in the slides, yeah, I'll make those available. But yeah, thanks for having me, guys. Have a great day.
Thank you to you. Have a great day to you too. Bye, everybody.